What specific problem does WebLLM aim to solve regarding the deployment of large language models, LLMs?
WebLLM aims to solve the problem of deploying large language models, LLMs, efficiently in web browsers, addressing three key challenges: the need for a standardized API for easy integration, adaptation to the browser's runtime environment, and achieving efficient GPU acceleration. By providing a JavaScript framework that allows LLMs to run locally in the browser, WebLLM enables web developers to incorporate LLM capabilities into their applications without requiring server-grade hardware. It leverages technologies like WebGPU for GPU acceleration and WebAssembly for CPU computation, ensuring high performance while maintaining a smooth user interface through the use of web workers. This approach not only preserves user privacy and enables personalization, but also facilitates hybrid inference models that combine cloud and on-device processing. Overall, WebLLM enhances accessibility and performance for LLM deployment in consumer devices.
How does the proposed WebLLM system work? Illustrate the workflow step by step from instantiation to inference.
The proposed WebLLM system operates through a structured workflow that begins with the instantiation of a lightweight service worker MLC engine in the web application front-end, which acts like an endpoint. Once instantiated, this engine loads the specified large language model, LLM, and is ready to accept OpenAI-style requests at any time. When a request is made, the front-end engine communicates with the back-end MLC engine, which runs in a web worker to handle the computationally heavy LLM workloads, ensuring that the user interface remains responsive. The back-end engine processes the request using efficient WebGPU kernels for GPU acceleration and WebAssembly for CPU tasks, allowing for high-performance inference. Finally, the output is streamed back to the front-end engine, which formats it as an OpenAI-style response for the web application to utilize, completing the inference process.
Can you provide a simple yet illustrative example of how the service worker MLC engine communicates with the MLC engine and processes an LLM request?
The service worker MLC engine communicates with the MLC engine through a message passing mechanism, where the service worker MLC engine acts as a lightweight front-end engine exposed to the web application. When a web application sends an OpenAI-style request, the service worker MLC engine forwards this request to the MLC engine, which operates in a separate web worker thread to handle the computationally heavy LLM workload. The MLC engine processes the request and generates the output, which is then sent back to the service worker MLC engine. Finally, the service worker MLC engine streams this output back to the web application in an OpenAI-style response format, allowing the front-end to update accordingly. This design ensures that the UI remains responsive, while the LLM inference occurs in the background.
What are the theoretical or practical benefits of deploying LLMs in the browser using WebLLM compared to traditional server-based implementations?
Deploying LLMs in the browser using WebLLM offers several theoretical and practical benefits compared to traditional server-based implementations. Firstly, on-device deployment enhances user privacy by processing data locally, which is crucial for sensitive information. Secondly, it allows for personalization by utilizing local data, enabling more tailored interactions. Additionally, WebLLM's architecture supports hybrid inference, where both cloud and on-device resources can be utilized, providing flexibility in resource management. The browser environment is universally accessible, requiring no additional software installation, which simplifies user access and integration for developers. Finally, WebLLM achieves up to 80% of the performance of traditional server-based systems while leveraging efficient technologies like WebGPU and WebAssembly, making it a compelling alternative for LLM deployment.
How is the WebLLM method validated or tested in terms of performance, and what datasets or benchmarks were utilized for its evaluation?
The performance of WebLLM was validated through a comparative evaluation against MLC LLM, specifically measuring decoding speed on an Apple MacBook Pro M3 Max. The evaluation was conducted using WebLLM version 0.2.75 running on Chrome Canary 133.0.6870. ARM64. The results indicated that WebLLM maintained up to 80% of the decoding speed of MLC LLM, which utilizes Metal kernels alongside a Python and C++ runtime. Although the specific datasets or benchmarks used for this evaluation are not detailed in the provided text, the focus was on decoding speed as a key performance metric. The evaluation also highlighted opportunities for further optimization of WebLLM's runtime and the potential to leverage new WebGPU features to enhance performance.
What limitations or drawbacks are associated with the WebLLM approach in terms of performance or applicability in various environments?
The WebLLM approach faces several limitations regarding performance and applicability. Firstly, while it achieves up to 80% of the decoding speed of MLC LLM, there remains a performance gap that could be addressed through further optimizations of WebLLM's runtime and the utilization of recent WebGPU features like shuffling. Additionally, the reliance on WebGPU presents challenges, as it lacks accelerated GPU libraries for common kernels, making it difficult to write high-performance customized GPU kernels such as page detention and flash attention. Furthermore, the implementation in JavaScript, while beneficial for browser compatibility, may not match the efficiency of traditional C++ or Python-based LLM inference engines, potentially limiting its performance in more resource-intensive environments. Lastly, the need for web workers to handle heavy computations could introduce latency in communication between the front-end and back-end engines, affecting the overall responsiveness of applications using WebLLM.